Today I'm going to share the work of support generation for additive manufacturing. Uh, this is the today presentation outline. To start with, support structure is known as a necessary evil because on one hand, it serves the purpose for printability, part balancing, thermal dissipation, but on the other hand, this is some extra material that you need to remove at the end. So you create additional work, increase the labor and also material cost, and you also have potential and the risk damaging the model. So there are different ways to try to minimize the harmfulness of the support. In the support minimization, that could be something like you can change the shape, like from this one. Originally, you have a lot of support need to be made, but if you change the shape, become something like that, then you can reduce the support. There are different types of support generation. Lattice reticle array is something like this. It's more like a reticle extrude directly from the support points to the platform. Tree-like structure is one of those minimizing the material, learning from the nature, to grow the branches and touch the support. However, there is still a problem is that no matter which support generation that we are doing with, those ponds outside the model are fine. You can easily break them away. But for those support ponds that are inside certain cavities, concavities, then you have trouble. You are very difficult to remove. For example, linear support or tree support. For the outside, you can easily remove it, break it by hand, but for the inside, it is very difficult with them. So over here, there is certain observation and also some objectives. The objectives is we want to reduce the number of contact points because the more the contact points, the more damage or the more difficult that you can remove the support. And the support shouldn't be fully covered by the concave features. There is some observation from the tree support you can see is that for the top part of the support, you have nowhere because you need to contact it. If you don't contact, you're not supporting it. So there's nowhere. You must be in contact of the model. But for the base here, you could be either on the model or you can on the base platform. If in case, if all the base for the support, all the base can be built only on the build plate, then first you can achieve two things. One is you fill the contact points because you have less contact points on the model. Secondly, the support will, because you are on the build plate, that means it is outside the model. Then you will, at least part of it will be exposed to the outside. Then you may have some ways to get them out from the model. Generally, tree support by itself is already NP hard, at least NP hard. How we can generate a support that can go outside from the concavity and then build on the build plate. That is the challenge that we want to solve. A heuristic way is developed. First, we classify all the support points to three types: the clear, obstructed, and enclosed. For clear, what does it mean is that it is something there's nothing beneath it. You can directly extrude it to the build platform. That means it is clear. Obstructed, meaning that it could have the potential to connect to link or to go outside and get to the build plate, but it need to move, it to be displayed, or it has a certain particular linkage to do so. It is not directly you can extrude it that. For enclosed, meaning that you have no way, no matter what you do, like something inside the whole model is surrounded, circled, there's no way. There's the only way that you can do is add support onto the model. So after having these three categories, then what to do is, the idea is a divide and conquer algorithm is to link the obstructed points to the clear points. Once you do it, then the obstructed will become clear. And if everything's done in this successfully done, then you will seem to be like, oh, the obstruct point have some linkage like escape from the model and become clear. So that is why this methodology is called the escaping tree support. So the overview is like here. I will talk about it in more detail step by step as a methodology. Before I go into it, I just want to name some notation terminology. If when you see a T, it is the layer thickness. When you see a S, it is talking about the cell support length. When there is a theta, basically S and theta are related. Is the talking about overhand angle. That means what is the maximum angle of the slope that you become an overhand that you need to put support. Support clearance C is talking including everything like the support diameter. That means how far you need to move away from the model, and also like the gap, you want to have certain gaps between the model and support, blah blah blah. So it will be included in the C over here. In the very beginning, the first thing for the input model, maybe an STL triangulated model, we'll do a ray tracing to become a ray-based representation. So one model, you will be becoming a set of rays and the sample points on the ray. Why good? Because the computation was very fast. And this checking can be done in a constant capacity. So that will be very efficient in this computation and in the process. This ray tracing algorithm from the model to generate become this whole representation will very fast. Full rasterization less than 0.1. So how to use it? For example, if we want to identify the support points, what are the points that we need to check, or what are the points we need to support? First of all, we just need to check the P-in, all the P-in point here, all the P-in points here. P-out we don't need to check because it is pointing upward. We don't need to any support. We just check the P-in. For each P-in, then if it needs to be supported or not, we check the self-supported region center or at this P-in. If there is any material in the same layer and also believe this layer, then that means it is self-supported. So by doing in this way, very quickly, just go for all the points, checking the previous layer using the range representation, then we'll be able to identify which P-in points need to be supported, and it will be used in the next step. So in the next step is the classification. So for example, we have 3 points here, the green one here, red one here, and the blue one here. All of them, because we have certain offset before we doing things. Most of the time, we offset a certain distance from the normal direction. So we also have 3 offset point here. So the goal over here is to see if this 3 point is clear, obstructed, or enclosed. The idea here behind is that we are using a bottom-up approach. We grow a visible region. So the process is like this, starting from the very beginning. For the build plate, the whole build plate is self-supported. So the whole thing is yellow. Then applying an erosion algorithm, then we find out that, okay, here you have a model. So I don't put any, you cannot put any support here. So we put support. This is the green region, the visible region that you can put support. So going through, so from this visible region, going to the self-supported region, the yellow here, we go ahead and then we find out what's the visible region, and then similarly go through all of them. So once we go ahead and then get the yellow region of the whole layer, but due to the fact that this model have change in topology, then you have 2 visible region like this one, and then we find that there is a point in this layer. Once we know that this is inside the green one, then this point is clear. And similarly, it keep on going, and then we will find that the whole visible region is the green region here, where you can put support. So this point, you are not inside the visible region, so it classifies that and close that. And this point, you are in the visible region, then this is just obstructed. This is not clear because you cannot directly issue down to the build platform, but it is still within the visible region. That means there should be a path you can come outside and get to the build platform. So this is how we classified it. So after this classification, the next step is during the generation of the support. So as mentioned, we will divide it into different subregion. This is the divide and conquer method. Basically, you have different support problems, we group them, and then we enlarge it group. And in this way, is that in each group, there is different configuration. We try to link from the obstructed to the clear. And in this case, there are 3 different cases. Like this is obstructed, this is obstructed, and the clear one is in the middle. Then we go ahead, go into the middle. If this is also obstructed. This is a clear point. Then you go into the clear region. Similarly, this is the right triangle type, obstructed, but this is very far away from these two. Then it's more like a right triangle type that this one is vertically going down, and then it go touching the clear region. So by doing so, the iteratively, all the region will be processed. At the end, the obstructed points will become clear. And this is the goal. So this is one of the illustration over here. This is an F model. So we also applied a top-down scanning process. How that is done is that we do it like from the top-down way. So we first process the top one. If we group them, and then we know that there's this level, and when we group it with the next level that is overlapping, then we stop there. We process the first level first. When we process it, then we bit by bit construct the support. This in the first iteration, and then go ahead and construct it, grouping it, and then construct something like this. And then in the second iteration, then you start to process. Over here, it stopped it because if we connect it to anything, it will create any intersection. So it stopped here for the first iteration. And for the second iteration, you go to the second level over here, and then you can build the grouping the support, and then grouping it like this. And this is the end of the second iteration. So it processes all the things done. And afterward, it will just extrude because all the points here become clear, and will extrude to the build platform, become something like this. And you can see that it is all the support can successfully build outside the model without touching any of the top surface, compared to some existing method, mesh mixer, which generating the tree support. It actually has the option to allow or disallow this kind of so-called the top connection, meaning these are the top connection. However, if you allow top connection, you will build support on top of the bottom surface here. But if you don't allow it, because it cannot search a solution, it just simply remove all the support over there, which is obviously not a valid solution because you cannot print a model without support by this way. We also, a lattice board is also tested, which is having a lot of like holes on the surface. While building the support, you can see that it successfully can be building the support going through and touching the build platform through the holes rather touching the board surface. A dental model is also shown, and the support is also built outside the model without touching the critical features on the model, reducing a lot of contact points in this case as well. The mushroom model shown in the very beginning, remember for the linear support, there's a lot of support trapped here. Also for the tree support, a lot of things cannot be removed inside the cavity. But for the ET support over here, you can see the support while it is building connecting, it go out and then connected with the support with the outside ones. There is no contact points inside the inner surface. So everything is connected to the build platform. And by removing it, because there is a connection over here, by shaking it a little bit and using a forceps, it is okay that we just directly pull out, draw out the support without damaging the model. And you can see that all the supports are clean and clear. Finally, I would like to show you the times statistic. I also use different like sub-process as well. This is talking about the identifying the support point. Here is the classification and also the support generation. This is the total point. In compare with the tree support generated by the mesh mixer, you can see that they have very different time different due to the capacity of the model. Thanks to the ray tracing algorithm and also the representation, all the models, regardless of the complexity of the shape, they do in the same way and very quickly. Auto one, remember. So all the things processing is very quick, and the total time, you can see that the total time, all of them is around just 1 second. So to summarize, a new support is developed in this presentation, in this research. It's named the Executing Tree Support. It's trying to build all the support onto the build plate to minimize the number of contact points. I hope you like it.